Hello, my name is Darren Thomas, and I am the Director of Educational Research Techniques. In this video, we're going to look over how to do division with radical expressions. So let's begin. Now, the first thing that we have to keep in mind is something called the quotient property for radical expressions, if you will. And just to give you an example of what that basically means is as follows. Again, we're going to do an example instead of talking about it theoretically. If I have, let's say, the square root of 25 over the square root of 25, this can also be written as the following. You could put everything inside a radical like this, 25 over 25, like so. Now, if you don't believe me, you can test this for yourself. So, to make it simple, the square root of 25 right here is going to be 5 over 5, which is going to equal 1. That's dealing with this guy right here. And again, if you do the same thing over here, square root of 25, well, of course, you do the stuff inside the radical first. So 25 is 1, and the square root of 1 is, 1. That's it. So this is an important principle to keep in mind as we go through the examples in this video. So let's move on now and do a real example here. So let's say I have the following. I have the square root of 50x to the third power here, and then I have underneath that the square root of 128x. Just call it x like that. So we already know that we can change this using the quotient property as follows. You just put one big giant radical like so, and then inside that you have 50x to the third power over 128x. Now, to have success doing this, you have to split things apart and find, common factors, and then you can eliminate those. Again, let's not spend a lot of time talking theoretically. Let's show it. So I have my giant radical again, like so, and then I got my, division sign here, my fraction, if you will. And so I'm going to deal with this 50x first. So in my mind, this is kind of what I'm seeing. I'm seeing 2 times 25, because that'll give me 50. Then I have my times x times x times x. Now again, you might not always draw all the variables here, but I'm going to do that for this purpose. And then underneath that, I'm going to have, let's see here, I will start with 2 times 64 times x. Now, there's a particular reason why I chose these numbers. Here's the thing. 25 and 64 are perfect powers. In other words, I can square root those and get a complete whole number. And so what we do now is that we eliminate like terms. So you can see here I have a 2 above and a 2 below. I can eliminate that. I have an x here. I have an x below. I can eliminate that. That gives me the following leftover answer here. I have giant radical sign again. I have 25x squared, and I have 64. And I already mentioned this, but I'm going to say it again. The reason I didn't factor the 25 and the 64 is because they're perfect powers. So remember, my index in this particular situation, the index is the little number that goes right here. In this case, it would be a 2, but we never write the 2. We only write the index if it's greater than 2. These numbers here have a perfect power. In other words, there's a whole number that I can multiply itself by to get 25. You guys know the answer for that. And the same thing for 64. And so now when I reduce this entire thing right here, I would get the following answer down below. And so my final answer is going to be 5x over 8. You can see that because the square root of 25 is 5, the square root of x squared is x, and the square root of 64 is 8. And this is my final answer right here. You can see not too difficult. Let's do a few more examples before we conclude this video. So here we go. Here's another one, slightly different. And we're looking at the cube root now. The cube root of 56 times a, like so, over the cube root of 7a to the fourth power. Now, using the quotient property, we've talked about this. I get my giant radical sign, cube root here, and I have 56 a over 7a to the 4th power, like so. Now I just, again, factor this in ways that fulfill my purpose. Now I need a perfect cube. I need a perfect power that when I multiply it by itself 3 times, I will get an answer here. So let me see if I can show you how I would do that. Again, it's sometimes trial and error in terms of finding the correct answer. So we got our giant cube sign again, giant radical. And here's how I would split apart the top part. 8, that's going to be valuable in a second, times 7 times a. So 8 times 7 is 56, 56a. On the bottom, I have 7 times a times a times a times a. Now I'm just drawing all the individual variables for the sake of purpose here. Now, what do I get as my final answer here? Because I'm getting close to this. So the 7's cancel out, and one set of a's cancel out. So I end up getting this answer right here. I end up getting the giant radical sign with the cube root here, and I get, looks like 8 over a to the 3rd power. And so when I simplify that by removing the radical sign, you should get the following: 2 over a. Now why 2 over a? Because the perfect cube, the perfect power when you cube 8 is 2, because 2 times 2 times 2 equals 8. And of course, when you raise a to the 3rd power, cubed is going to be a. Again, this is something we discussed before. And so this is my answer. Let's do one more, this time with 2 variables. So this one, it looks ugly, but if you think about it for a few seconds, it's not too crazy. Let's take a look at this and see if we can make it clear. So here we go. The square root of 162 x to the 10th power y to the 2nd power. Then we divide that by the square root of 2x to the 6th power y to the 6th power. So again, I use my quotient property here, so I get a giant radical sign, and I put everything underneath it as before. 2x to the 6th power y to the 6th power. Now, what do I do next? Of course, I factor things as appropriate. And so what I end up with is as follows. I end up with giant radical sign again. I end up with, over this, I end up with 81. That'll be useful in a moment. Times 2 times x to the 10. I'm not going to draw out 10 x's, obviously. Times y to the 2nd. And then I'm going to have 2 x to the 6 and y to the 6, like so. Now, you can already see here some basic elimination. This is going to eliminate, like so. The 10x, the x to the 10th power and the x to the 6th power is going to become x to the 4th power. I'm going to put that over here for now. The y to the 2nd power and the y to the 6th is going to become y to the 4. That'll be down below, like so. And then, of course, we'll still have our 81. That's what we're going to have. And all this is going to be in a giant radical sign. So what happened is this: 10 minus 6 is going to be 4. But over here, we're going to do 6 minus 2, and that's going to be 4. So y to the 4, x to the 4. The 2's cancel out, and the 81 is still there. Now, when I square root everything, you should probably already know what the answer is going to be. So the square root of 81 is going to be 9. Oops, excuse me. I need more space. Square root of 81 is going to be 9. Then we're going to have x squared. And all that is going to be over y squared, like so. And this will be our answer, like so. And so you can see that's how that works out. So you can see that, this is not too complicated once you're familiar with the steps and you understand the process that needs to be done. So let's go back and review and see if we can try to make this as clear as possible. So we began this video by taking a look at the quotient property for, radical expressions. And simply it just means that when you have a radical expression, we have a square root above and a square root below, you can put all that information inside one radical. Now this is of course assuming that the numerator and the denominator radicals have the same index. If it's not, it's going to be something slightly different. And so here's the proof here. You can look at that. You can see it's clear. It's the same answer either way. Then we actually worked out an example here. And so in this example here, we can see that we first used the quotient property to put everything under one radical, and then we just factored as appropriate, always searching for that perfect power that we can use. But what we mean by that in this situation, something that when we square root it, we get a whole number. And so by going through this process of eliminating like terms and then doing the square rooting as appropriate, we're able to get the final answer here. And of course, we repeated this, but in this example, we had a cube root rather than a square root. But you can see all the same process was used in this particular example. Okay. And then lastly, this is our last example. We just had something a little bit more complicated. We had, two variables instead of one and a slightly larger number. But again, if you're familiar with, looking for the right patterns, again, it's not that deep in terms of how to do this and how to address these different problems. So I hope that this video was useful for you and that you were able to understand and appreciate, what we talked about here. My name is Darren Thomas. I'm the Director of Educational Research Techniques. Take care.